Hello everyone. Today I will talk about STELAR, spatio-temporal tensor factorization with latent epidemiological regularization. So this is a paper published at AAAI 2021, and it's a joint work by Nikos Kargas, Cheng Qian, Nicholas Sidiropoulos, Danica Xiao, Lucas Glass, and myself. So the task is about epidemic prediction. And the setup is the following, right? Given this three-way tensors, location by signal by time, and we want to predict what's going to happen at the future times. And for each of this location by signal position, right, if you look at this over time, it's give you a time series. For example, at the location in New York, and for a number of new cases, if you plot this over time, you see some curve over here. And for a different location, LA, for ICU visit, you can see another time series. Right? So if we organize all this time series as the 3D tensors, the goal is to predict what's going to happen in futures, right, for all those locations and all those signals. And so this is, yesterday I talked about another paper, STEM, doing similar things with neural network-based model. And this is a different method using tensor factorization for doing a similar task. So here's a quick preview of what we will talk about. We introduce the method, which is a tensor factorization-based method for predicting the evolution of pandemic trends. And we'll show you some experiment on predicting case at county level and state level. And I'll show you, this type of method, tensor method actually perform better. And it also can review interesting latent patterns. So let's get started. Let's first start talking about some related work. So there are a lot of mechanistic models, those epidemiological models, such as SIR model, SEIR models. And all these models rely on a number of differential equations. They do not require much training data, but it's also very restricted because you cannot leverage rich observational data. On the other hand, machine learning models such as neural network or time series based model, and they are learned from data, but usually require a large amount of data, and oftentimes those resulting models are black box without a clear interpretation of why certain predictions are made. And in this work, we introduce a non-negative tensor factorization-based method, and can leverage the latent epidemiological dynamics, in particular this SRI model. And it can learn from limited data and can also extract interpretable latent components. So there's, let's start. There are, the building block for our method is this canonical polyadic decomposition method, CPD. So CPD decomposes a tensor, for example, this three-way tensor, X, as the sum of k rank 1 component, right? Each one of the rank 1 component is an outer product of three vectors. And if you organize those vectors into matrices, you will get those vector matrices, A for location, B for signals, C for time. And then there's a different view of this tensor. I can have element view, matrix unfolding view, or vector view. Another building block for our model is this SIR model. So it models the susceptible population, infected population, and recovered population, and how they change over time. And for example, they just specify a number of differential equations look like this, and by setting two different parameters, the rate of spread beta and the recovery rate gamma, then you can simulate how this different population change over time. And in particular, this spread beta affects both the infected population and the susceptible population. It's modeled as interaction between these two populations, and the gamma affects the infected population, so that's give us the recovered population. So one important measure here we cares about is the number of new cases, or CT. That is the beta times st minus 1 times it minus 1 divided by total population n. And in practice, we do observe CT, and so we just want to fit IRR model, also kind of for the CT as well. So if we are given model parameters such as initial susceptible population, maybe 95%, initial infected population 5%, and the recovered population 0%, and this beta and gamma coefficient, then you can simulate how those different populations are changing over time. So that's SRI model. So key idea behind STELAR is to model this different location, different signals together. And if we look at the tensors, right, so we have this tensors, and the goal is we first have this CPD models, right, with sum of rank 1 components. Then we put some additional constraint using SR constraints on the time components, right? If we have a K latent vectors, then the time components can be also modeled with K separate SR models, such as this. So here's the entire problem formulations. And so we want to optimize, we want to minimize this particular loss function. It has 3 parts. The first part is the data feeding terms, right? The difference between the original tensor and this CPD tensor. And then we have this normalization, this regularization term on the factor matrices A, B, and C. So we don't want them to be too big. And then the most interesting part here is this SR model regularization. So we want to also constrain the component C, right, for each of these latent vectors. So we have a K of those, and as K different SRI models. So once we learn this model, so we will have the factor matrices A, B, C, and all these different SRI parameters as well. Then to do prediction, we first predict the latent vectors on the time mode, right, C, T hat, using the SRR model. Then we can predict the entire future slab on the tensors by using just this matrix operation, A times diagonal matrix of this vectors CT hat and times B transpose. So a little more details on this prediction, right? If you think about this in element view of a tensor, and it's really a sum over of this product of 3 elements, right? A mk times b nk times ctk. Right, this ctk is actually modeled with the SRR model, right? This beta k times s t minus 1 times I t minus 1. So this is how we model the each element, right? It's this term A and B actually modeled the interaction between location and signals, and then the last part is actually kind of a sum over K separate SRI model. Okay, so you can also do this using a matrix operation. Then actually different component of C follow a different SRR model. So optimization for this is we use alternating optimizations by fixing everything else and optimize A. Then the resulting subproblem become a non-negative least square problem. Similarly for B and C. Then for SRR models, we rely on projected gradient steps. So that's the optimization step. So next, let's talk about experiments. So we have a data set that based on the data from Johns Hopkins University. Those are the live tracking data for COVID cases and hospitalization. And we also have the claims data from IQVIA. And we use daily counts of 12 different ICD-10 codes at each county or state level. Then we'll also use a CPT code related to hospitalization and utilization of ICU. So number of counties here in this data set is 133. Number of signals are 15. And we use the time window from late March to late June. So 95 days of data. So we have 2 different experiments. One was 85 days for training, 10 days for test. And the second experiment was 80 days for training and 15 days for test. So the metric is root mean square error or mean absolute error. So here's the county level prediction result. And you can see that for 10 days prediction or 15 days prediction. And all these measures are the lower the better. So you can see that STELA's performed the best, and compared to a whole set of baseline method, including the epidemiological models, SIR or SEIR, and time series, some neural network type of models, and LSTM-based model, and STEM. That's another neural network-based model specifically designed for predicting COVID cases based on spatial-temporal data like what we are using here. And similarly, the performance, there's a significant gain in performance on hospitalization as well. And so that's for the county level prediction. State level prediction, very similar trend observed. Actually, for state level, STEM performed pretty well for new case prediction, but for hospitalization prediction, STELA's performed better. And not only we got better prediction, the result can be explained as well. So if we plot the several SR models, we can actually see different progression of pandemic evolution, right? For example, component 1, it peaked very early on, like 10 days into this, and component 2 peaked much later, right? So it's close to 80 days to reach the peak, and component 3 is somehow in between. And if you look at the corresponding locations, it also makes a lot of sense, right? So New York, Florida, corresponding to the component 1, that has an early peak in this pandemic, which makes sense because in the United States, that's how the COVID pandemic happened, right? In New York, Florida, it happened first, then it quickly progressed to other states. And for the second component, right, covers broadly many other states. I mean, we can view this as maybe the entire country, right? California, Illinois, Wisconsin, and so on. So that's actually reached the peak 80 days later. So that's getting close in May or June time. I think it's in the May time frame. And then if you look at the corresponding component for the signals, they actually share pretty much the same thing for all different components, which makes sense, right? Because once the pandemic happened, right, the type of behavior is very similar. That's why new cases, hospitalization, ICU utilization, and the corresponding common diagnosis code happen in all components. Okay, so that's the interpretability result. So in conclusion, we propose STELA, a data-efficient interpretable method based on constrained non-negative tensor factorization. And this method can predict long-term prediction for future timestamps by incorporating both the data and the latent epidemiological regularization. And we demonstrate the ability of STELA to make accurate prediction on real COVID dataset. So that's it. So this is the STELA paper published in AAAI'21, and special thanks for Nikos Kargas for providing such a nice slides for me. And thank you very much.